Hello and welcome again to another series of lectures in functional analysis. So to start, we will discuss the so-called projections. And as our motivation, we consider the following proximal problem, and we restrict this problem in the case of a Hilbert space. So the problem is the following. Given a Hilbert space X, an element small x in this Hilbert space, and a non-empty subset A of X, we would like to determine if there exists a point in the subset A that is closest to the given point X. So you can think of this as looking for a point in the subset that is closest to the given point small x. To have an illustration, let us consider the situation where X is our Euclidean plane, R2, and consider these two subsets of A. So here we have a rectangle where one side is open. So in this example, your set is not closed. And when you pick this point x1 here, you see that there's a point, let's say a1, that is closest to x1. And in this case, you can take this point on the boundary. And in fact, in geometry, we know that since we have here a straight line on this edge, then this line connecting x1 and a1 should be perpendicular. However, there's a problem if you, for instance, take x2 on the right of the side where the side is open. So here, you cannot find a point in A that is closest to x2 because the boundary on this part, the right boundary is not included. So you can get close and close to the boundary, but you can still find something that would have a lesser distance. However, you cannot attain the smallest distance. Okay, because here is the closest point in the plane to the point x2. So this is a point closest to x2, but this point is in R2, but not in A. So in this case, if your set is not closed, then it is possible that you have non-existence. Next, let us consider a point here, or as the set A on the right, this quadrilateral. And if you pick at the point x1 again, you can find a point a1 on the boundary. And since this is a straight edge, this line passing these 2 points x1 and a1 must be perpendicular as well. The problem occurs when you have an x2 here. Okay, so now our set is closed, but in this case, it is not convex. Okay, since here we have 2 points on the set, namely this, let's say this 2 points here on the edge, the vertices of the quadrilateral, the line passing through these 2 points does not lie in the set A. So you have a non-convex set. Okay. So as I recall, note that a subset A is said to be convex if for every 2 points, let's say x1 and x2 in A, the line segment passing through these 2 points must be a subset of A, or must be contained in A. Well, to write that mathematically, given these 2 points and let's say a parameter lambda between 0 to 1, the convex combination lambda x1 plus lambda 1 minus lambda x2 must be also in A. Okay, so this is basically the line segment passing through x1 and x2. So if lambda is equal to 1, you have x1, and if lambda is equal to 0, you have x2. Okay, we excluded already the endpoints because we know that x1 and x2 are in A. So as lambda decreases, you go in this direction. So as lambda decreases to 0, you pass through the points on this line from x1 to x2. Okay, so that is a convex set. If any 2 points on the set, the line segment passing through these 2 points lies in the subset A. So in this case, our set A is not convex because, as I said, if you pick these 2 points, the line segment is not a subset of A, or is not contained in A. And if this is the case, although you have these 2 points as closest to x2, okay, they are not that point is not unique. So here we have 2 points that are closest to x2. So non-convexity may imply non-uniqueness. So going back to our proximal problem here, so it seems that if you want the existence of a point and a uniqueness, and the uniqueness of that point, we need the subset A to be close and convex. And in fact, this is the case. And this will be the content of our next theorem. So let's start with the assumptions again. So repeating the assumptions in the proximal problem. So let X be a Hilbert space and consider a non-empty subset of X to be closed and convex. Then, for each X in the Hilbert space, there exists a unique point A. This might depend on X, so let us emphasize that with a subscript. So there is an element, a unique element, A sub X, in the closed and convex set, such that the distance between the point X and AX is also the distance of the point X to the set A. So recall that the infimum here, or the distance of, between a point and a set is the infimum of the distance between X and elements in A. So that is the definition of the distance of a point and a set. The infimum of the distances of X at any point on the set A. So in particular, this implies that the infimum is attained since AX is in A. Hence, I can write this also as the minimum of the distance between X and the points in your set A. So the infimum is attained, therefore it is a minimum. Okay. So moreover, if let's say X is in A, okay, what if your set, okay, is in A? Or what if your point X is in A, then AX is also in A. Or I should say AX is equal to X. Of course, if your point is in A, then the closest point in A to it must be itself. And in that case, the distance is 0. Okay, so let us take a look at the proof of this theorem. So we again split the proof into parts: existence, namely existence, and uniqueness. So to prove existence, okay, first let us denote by D, for simplicity, the distance between the point X and the set A. So as an illustration, consider this set A, okay, and a point X. Let's say that is not an A, or without loss of generality. Okay. So this distance is this line segment. Okay, so here we visualize the situation in the Euclidean plane, just to have an intuition of the idea of the proof. So this D here, the length of this line segment, so you can think of this as the distance between the point and X. Well, you can choose that if, let's say, geometry, if you have this tangent, so that you have this tangent and this line to be orthogonal or perpendicular. Okay. So now, here, you would like to construct a sequence, okay, in the following way. So pick a point, let's say A sub n, wherein the distance between X and A n is, let's say less than. So the distance here, let's say this line segment is less than d squared plus 1 over n square root. Okay, so this number is less than d. Okay, obviously it's less than d, and this is guaranteed by the definition of the infimum. So in that case, we will have the following. So given, or for each n a positive integer, we can find an an in A such that the distance between X and an, okay, let's make that squared. Well, this is certainly greater than or equal to the distance, because the distance is the infimum. And this distance is less than, let's say, the square root of d squared plus 1 over n squared. So you end up with d squared plus 1 over n. Okay, we are guaranteed with this due to the fact that the distance d, or which we denoted by d, is the infimum. Okay, so if we have another, let's say, point am here with m greater than n, then take note that here we will have a smaller distance. So it seems that the sequence converges or tends to this point here. And in fact, we claim that this sequence is convergent, and it converges to the solution of our proximal problem. Okay. So first, let us establish that this construction of the sequence AN is in fact a Cauchy sequence. So to do that, let us first apply convexity. So by convexity of A, the midpoint, that is the average between these 2 points, must be also in A. So think of this, for instance, the point here. So this would be the midpoint of the two. Okay, now since this midpoint is also in A, then the distance of X and this point, EN plus AM, must be also greater than D by the definition of D. Squaring both sides, and we have this. Okay, you can write this as follows. So this is equal to, so we separate X into 2 parts. So we will have the following. So 1/2 of X minus AN plus X minus AM squared. And applying the homogeneity of the norm, this is equal to 1/4 of X minus AN plus X minus AN squared. The next trick is to, let's say, add and subtract a term. So here we would like to add the difference squared, the norm squared of the difference. So to compensate that, we subtract the same term. But here, take note that this difference, this X here will cancel, and you end up with AM minus AN, norm squared. Okay, now concentrating on this 2 terms here, after factoring 1/4, if I, let's say, let this to be W, and then this to be V, let's say, this is also W, this is also V, then take note that, okay, if we have the following, so the shaded terms is basically this sum of norm squared. Take note that the sum of the norm squared is the inner product of the vector or the element with itself. So expanding the inner product, you will see that the middle term will cancel, and you end up with the following equation. So a simple or a straightforward algebra leads to this equation here. And take note that this is basically the parallelogram law. Okay, so with this, we have the following equation. So continuing, uh, so we gain a factor 2, and since we have a denominator 4, we will have 1/2 the norm of w squared. So that is the norm of x minus an squared plus 1/2 times the norm of x minus am squared minus 1/4 am, the norm of am minus an squared. And from this, we see that uh, according to our construction of the sequence am, this one, so this can be estimated as follows. So this is less than 1/2 e squared plus 1 over n plus 1/2 d squared plus 1 over m minus this term, the last term. And from here, you can now see that this d squared will be cancelled for this part. Okay. And putting this on the left-hand side, we end up with the following estimate. So we have the norm of am minus an squared is less than, since we have a factor of 4 here, so we have 2 after multiplying 4 both sides, so 2 over n plus 2 over n. And clearly this tends to 0 as n and m tends to infinity. This means that our sequence is Cauchy. And so we can find a limit, okay, by completeness of x. So we can find an a sub x, let's say, in x such that an converges to ax by completeness of your Hilbert space. However, our assumption is that A is closed. So here we have a sequence in the closed set A, and it is convergent. Ax must be also in A. And now if we, let's say, pass n to the limit in this equation here, okay, you apply the squeeze theorem, and then you take the square root of both sides. You end up with the following. So the norm of A, or I should say x minus ax, this is the limit as n goes to infinity of the norm of x minus an. And we said last time that if you apply the squeeze theorem and then take, let's say, the square root both sides with these equations or set of inequalities in star here, you end up with the limit of the distance between x and an as n goes to infinity to be d. Okay, and take note that this d is the distance, therefore we have established existence. Next, let us discuss the uniqueness of this point. And we proceed in a standard manner. In other words, suppose that I have, let's say, 2 elements, say ax and bx, that satisfies these equations. Suppose we have 2 points that 2 points in A that is closest to X. Now, if we, let's say, replace AN and AM by AX and BX in our previous computation, okay? So you can still adapt this computation here, and we will specifically use this inequality here. So if you use that, you end up with the following. So d squared is less or equal to 1/2 x minus ax, norm of ax minus norm of x minus ax squared plus 1/2 of norm of x minus bx squared minus 1/4 ax minus bx, or I should say bx minus ax squared. Now, from these equations here, we end up with the following. So this is 1/2 d squared plus 1/2 d squared for these two, and then just copy the last term. Again, you can see that you can cancel d squared both sides, and then after putting the norm squared on the left hand side, multiplying by 4, and then taking the square roots, we know that the norm is less than or equal to 0. However, the norm is non-negative, so we can replace this by b of x minus ax equal to 0. By the definiteness of the norm, this implies that ax must be the same as bx. And that is the proof of your uniqueness. So there must be a unique point that is closest to x. So from this theorem, we define the so-called projection map denoted by P sub A so this P sub A of x, let's say, is equal to A sub x if and only if A sub x is closest to the point x. So in other words, the distance between x and ax is the same as the distance of the point x to the set A. And this projection map is well defined. If A is closed and convex, take note that given an x, there is a unique A sub x in A that satisfies this property, according to the previous theorem. So in the following theorem, we provide an alternative characterization of the projection map on a closed and convex subset. So again, let us consider a Hilbert space X, a non-empty convex and closed subset A, a point X in the Hilbert space, and a point Y in the closed and convex subset. Then Y is the projection of X onto A if and only if the real part of the inner product between x minus y and a minus y is less than or equal to 0 for any a in the set capital A. To have an illustration of this inequality, and by the way, this is called a variational inequality, since this inequality varies on every element of your subset A. So suppose this blue region here is a portion of your set A. You have a point X outside A and a point A inside A. Then this Y is the projection if and only if, okay? So for instance, in the real case, so the real part would be the same as the inner product. So this means that the angle between the vector x minus y, and that would be this vector, and the vector a minus y must be, so you can think, as we said, as the inner product. You can think of the Euclidean inner product as multiple of the cosine of the angle between these two vectors. So if the cosine of the angle is less than or equal to 0, then the angle must be at least pi over 2. So a minus y would be this vector. So the angle, let's say theta, must be greater or equal to 90 degrees. Okay, so this should be, or this should hold on every point in A. So if you pick another point, so here you have another angle, and so on and so forth. So, and that is why this, well, if you have, let's say, a well-defined tangent at the point, then that tangent must be orthogonal or perpendicular to the vector x minus y. So let us look at the proof of this theorem. So let us take an element A and suppose that y is the projection of x. So here we are proving this direction. Now, for each lambda in the open interval 0 to 1, lambda A plus 1 minus lambda y. Take note that the projection maps a point in the Hilbert space to the subset A. So y is in A is in A, therefore this one is in A. So from this, let us take note that so x minus y squared, well, y is equal to the projection. So this must be x minus the projection squared And this is equal to the distance between x and the set A squared. And why is this? This is according to the definition of our projection. Since this convex combination here is a particular element of your set A, then the distance squared must be less than the distance between x and to this particular point. So lambda A plus 1 minus lambda y. And rearranging the terms, we have the following. So here you will have x minus y minus lambda A minus y. And if you expand this, you will have the following. So you will have the norm of x minus y squared minus 2 lambda times the real part. Okay. Take note that our form is a ciscollinear, so it can be complex valued. So here you should take the real part. Plus, okay, applying the homogeneity of the norm, you have lambda squared, norm of A minus y squared. Okay, and from this, so we can cancel the first term, put this on the left-hand side and divide by 2 lambda. Take note that lambda is positive. You end up with the following inequality. So the real part of the inner product of x minus y and A minus y is less than or equal to lambda over 2 times the norm of A minus y squared. Okay, so from here, since y and A are independent of lambda, if we now take the limit or pass to the limit as lambda goes to 0, from the right, we obtain that the real part of the inner product between x minus y and A minus y is less than 0. And since A is arbitrary, this is true for any A in your subset capital A. And you can see that this is in fact the variational inequality that we would like to establish here. So that's one direction. For the other direction, so suppose that the variational equation is valid. So first, let us take an element A. Then, by rewriting this difference x minus A as x minus y minus A minus y. So here we add and subtracted y. And then you calculate again or you expand, you will have the following equation. The norm is non-negative, and by our assumption, this real part here is negative, therefore including the negative sign here, this is non-negative. Hence, this term must be greater or equal to x minus y, norm of x minus y squared. Since this is valid for any A, we take the infimum. Over all A in your subset, you will get the following. So the norm of x minus y, here we already took the square root. So this must be less than the infimum x minus A. Take note that this is the distance by definition. However, according to our assumption, y is an element of A. So this must be greater or equal to the distance as well. So you are squeezed. So in fact, these inequalities are also equalities. And as a result, the distance x minus y is equal to the distance of x and A. And from the definition of our projection, we now conclude that x or y should be the projection of x onto A. And this is the reverse direction. So now let us add an additional condition on the subset. Namely, instead of convexity, we have a subspace. So consider again a Hilbert space X and a non-empty closed subspace A of X. Of course, obviously, a subspace is a convex subset of X. Likewise, take a point X in your Hilbert space and a point Y in your closed subspace A. Then the projection can be characterized as follows. So Y is the projection of X in A if and only if X minus Y is in the orthogonal complement of your subspace A. So as an illustration, let us consider X to be the three-dimensional Euclidean space, and your subspace must be, or your subspace is this a plane here. So you have a subspace with a codimension 1. So the orthogonal complement must have a dimension 1. And after translation, that orthogonal complement must be this line here that is perpendicular or orthogonal to the plane. And from that, if you have a point X not on the plane, then Y is the projection onto the plane if and only if X minus Y lies on this orthogonal complement. And that is the reason why we call it the projection. So to get the point closest to the plane, you need to project X onto the plane by creating or looking at the line perpendicular to the plane. And the intersection, in this case, let's say Y, would be the projection. So for those who are not familiar with the orthogonal complement, let us define this one. So A perp, the orthogonal complement, is the set of all elements in your Hilbert space wherein the inner product between X and A is 0 for any A in your set. So loosely speaking, these are the set of all X in your ambient Hilbert space, capital X, that is orthogonal to any element of the subset A. You can easily show that this is indeed a closed subspace of X. So you are encouraged to verify this. Okay, so here we have another part Moreover, the projection is also linear. So it's a linear map between these two vector spaces X and the subspace A. Okay, so let us take a look at the proof. Again, we need to establish two directions, and let us start as usual with this direction. So let us pick an element A, and let's say a lambda, or let's say beta, to be in K. So K here is the field of the real numbers or the complex numbers. If Y is the projection of X onto A, then we know, okay, just to remind ourselves, according to our previous theorem, and taking note that a convex subset or a subspace is a convex subset, we also have this variational inequality, let's say for A naught, for every A naught in A. So if I take a specific A naught, namely alpha, or I should say beta, okay, so let us remove this. We will pick a specific beta in the following argument. So it's not an arbitrary element. So beta, let's say beta A plus Y. So this is a linear combination of elements in A. Since A is a subspace, then it must be in A. And let us pick beta to be the inner product between X minus Y and A. So this is our beta in this linear combination. Then, if we, let's say, compute this term, so you end up with the following. So with this specific value of A naught, you end up with, so subtracting Y, you end up with beta A. Since the inner product is antilinear or conjugate linear with respect to the second component, so you have the following. So pulling out beta, you should put the conjugate. And take note that this is our beta. So therefore, you have the real part of the product of the conjugate of beta in itself, but that product is basically the modulus of the complex number beta squared. Since this is real, so we can ignore the real part, the notation for the real part, and take note that well, these are all equal, then this one is less than or equal to 0. So we conclude that this must be 0. Or equivalently, beta must be 0. But what is beta? Beta is X minus Y, inner product with A. And again, since A is an arbitrary element of your subspace, this is valid. So according to the definition of your orthogonal complement, okay, so X minus Y is orthogonal to any element in your subspace capital A, this implies that x minus a must be in the orthogonal complement of a. And that is this direction. For the reverse direction, so let us suppose that x minus y is in the orthogonal complement of a. Then x, the inner product of x minus y and a naught must be 0 for any a naught and a. Okay. For each a in capital A, if I take, let's say, a naught to be a minus y, and this is valid since a is in capital A, by the assumption of the theorem, y is in capital A, so this difference, since A is a subspace, must be also in A. And from this, applying this equation here, we end up with the following equation. So the inner product of x minus y and a minus y is equal to 0. Again, this is true for any a in your subspace. Since this is true, the real part also satisfies this equation. And from the previous theorem, this implies that y must be the projection of x in A. Recall in that theorem, we only need less than or equal. So that finishes the proof of this equivalence. With respect to the linearity of the projection, well, what we can do is, so let us take two elements, x and z in X, and a scalar alpha. Since x minus, let's say, PAX and z minus P sub AZ is in the orthogonal complement of A. And why is this the case? We have this, okay? So if y is equal to PA of x, you just replace y by the projection. So the difference of the point and the projection must be in the orthogonal complement. Knowing that the orthogonal complement is a subspace, this implies that the linear combination, so alpha x minus this difference plus z minus PAZ, this must be in the orthogonal complement as well. Of course, you can rearrange this as follows. So alpha x plus z minus the projections, the linear combination of the projection. Since this difference is in the orthogonal complement, this implies that this must be the projection of this linear combination in A, according to the first part. So therefore, we conclude that the projection of the linear combination is the linear combination of the projections. Hence, the projection is linear. In fact, one can show that the projection is also bounded. And bounded linear operators will be the topic of future sections. And that's it right now for projections. In the next lecture, we will discuss compactness or compact subsets of function spaces.